E equals mc square is the equation that shows the relationship between mass and energy. In this equation, E stands for energy, m stands for mass, and c square is the speed of light squared. Now, why is the speed of light involved? Well, the speed of light is an incredibly large number, about 300,000 kilometers per second. When you square it, you get an even larger number, making the equation quite powerful. This equation tells us that mass and energy are interchangeable. In other words, a tiny amount of mass can be converted into a huge amount of energy. This is why nuclear reactions, which involve small changes in mass, release enormous amounts of energy. Think of the sun, where nuclear fusion converts mass into energy, giving us light and warmth. So what is rest mass? Rest mass is the mass of an object when it's not moving. It's a fundamental property that doesn't change, no matter how fast the object is moving. Even when objects are moving at the speed of light, like photons, they have no rest mass but still carry energy and momentum. When mass is lost in chemical or nuclear reactions, it's converted into energy. This energy can be in the form of light, heat, or other forms of radiant energy. That's why nuclear power plants can generate so much electricity from small amounts of fuel. But how did Einstein come up with this idea? The concept arose from his work on special relativity, which deals with how objects move and interact at high speeds. He proposed that the equivalence of mass and energy is a fundamental principle of the universe grounded in the symmetries of space and time. This principle was first published in his 1905 paper, marking a milestone in the Annus Mirabilis, or miracle year, when Einstein published several groundbreaking papers. So E equals mc square is more than just a catchy equation. In special relativity, the mass of an object isn't as straightforward as it seems. When an object moves at different speeds in different frames of reference, depending on the motion of the observer, its kinetic energy varies. This implies that the amount of relativistic energy an object has is frame-dependent. Essentially, the energy measured depends on who's observing it and how fast the object is moving relative to them. The relativistic mass is given by the relativistic energy divided by the speed of light squared c2. Because the relativistic mass is directly proportional to the relativistic energy, these terms are nearly synonymous, differing only in their units. But what about rest mass? The rest mass, or invariant mass, of an object is the mass it has when it's not moving relative to the observer. This rest mass remains consistent across all inertial frames, meaning it's the same no matter who's observing it or how fast the object is moving. It's the smallest possible value of the relativistic mass of the object. Interestingly, the rest mass is almost never additive. This means the mass of an object is not simply the sum of the masses of its parts. The reason lies in the attraction between components of a system, which results in potential energy. The rest mass includes the total energy of all parts, including kinetic energy observed from the center of momentum frame, and potential energy. Particles with no rest mass, known as massless particles, have no intrinsic energy. Their energy comes solely from their momentum. So why does all this matter? Massless particles have zero rest mass, which means they don't have any intrinsic energy when they're not moving relative to an observer. But don't let that fool you into thinking they are insignificant. Let's talk about photons, the most well-known massless particles. The energy of a photon is given by the Planck-Einstein relation, E equals sign hf, where h is the Planck constant and f is the photon's frequency. This frequency, and thus the relativistic energy of the photon, is frame-dependent. What does that mean? Essentially, the energy of a photon changes depending on the motion of the observer relative to the photon. Imagine an observer moving away from a photon in the same direction it's traveling. As the photon catches up to the observer, it appears to have less energy than it did when it was emitted from its source. The faster the observer moves, the less energy the photon seems to have. This is due to a phenomenon known as the relativistic Doppler effect. As the observer approaches the speed of light with respect to the source, the photon's wavelength stretches out, increasing the redshift and reducing its energy. In theory, if an observer could reach the speed of light, the wavelength of the photon would become infinitely long, and its energy would approach zero. This occurs because massless particles like photons do not possess any intrinsic energy. Let's explore another fundamental idea, the conservation of mass and energy. In the realm of physics, the conservation of energy is a universal principle that applies to any interaction. This principle is tightly woven with the conservation of momentum, ensuring that energy and momentum remain constant in isolated systems. However, when we shift our focus to the classical conservation of mass, things start to get a bit more complex, especially in the context of relativity. In classical physics, mass was once thought to be strictly conserved. However, in certain relativistic settings, this principle doesn't hold up. Experimental evidence supports this, particularly through the conversion of mass into kinetic energy in nuclear reactions and interactions between elementary particles. In modern physics, the phrase conservation of mass has largely fallen out of favor. Instead, we often talk about the conservation of energy, which encompasses mass as a form of energy. Relativistic mass can be considered equivalent to the energy of a moving system, allowing us to understand how mass and energy are conserved in a broader sense. Mass conservation breaks down when the energy tied to the mass of a particle transforms into other forms of energy, such as kinetic energy, thermal energy, or radiant energy. Let's venture into the real world to see how the equation E equals mc squared is harnessed in modern technology. From nuclear power plants to particle accelerators, the practical applications of mass-energy equivalence are both fascinating and transformative. First, let's look at nuclear power plants. These facilities are a testament to the power of E equals mc². In nuclear reactors, atoms of heavy elements like uranium or plutonium are split in a process called fission. This splitting releases a tremendous amount of energy, which is then converted into electricity. The energy released in this process is directly related to the mass of the particles involved, showcasing Einstein's famous equation in action. Next, we turn our attention to particle accelerators, the colossal machines that propel subatomic particles to near-light speeds. These accelerators, such as the Large Hadron Collider, rely on the principles of mass-energy equivalence to probe the fundamental nature of matter. By smashing particles together at high energies, scientists can observe the transformation of mass into energy and vice versa, providing critical insights into the building blocks of the universe. But the applications don't stop there. Consider the advancements in medical technology, particularly in cancer treatment. Techniques like proton therapy and radiation therapy utilize high-energy particles to target and destroy cancer cells. The precise calculation of energy required for these treatments is grounded in the principles of EMC², ensuring that maximum damage is inflicted on cancer cells while sparing the surrounding healthy tissue. Moreover, the concept of mass-energy equivalence extends to our understanding of the cosmos. Astrophysicists use this principle to study phenomena such as black holes and neutron stars, where immense gravitational forces cause significant mass-energy transformations. These insights help us comprehend the life cycles of stars and the dynamic processes shaping our universe. In summary, E equals mc² is not just a theoretical concept, but a vital tool with practical applications that revolutionize technology, medicine, and our understanding of the universe.